was a couple questions that were brought to my attention, and we're going to get to them in 1 second. We make sure everything's, we're good. You can read that. We good here? We're good in, and hopefully we're good out for those Zooming at home. So the first question that was brought to my attention was, how do you integrate secant cubed from one of the previous homeworks? So questions. So the first one is how to integrate secant cubed. So this was on one of your homeworks. I allude, this integral is needed for many arc length integrals, amongst other things, and it's not easy to note. And we're going to talk about that in a second. And the second one was what numeric integration rules should you know? So we're going to answer both of these, and then we'll talk about your homework. And so if you have questions, please interject, whatever it takes. Fun times here at LaRoche. All right, so the integral of secant cubed it's quite a famous integral in the sense that it shows up in lots of places, and it even has its own Wikipedia page, which says something. So what I'll do is I'll give you sort of a hint on how to proceed. So to compute this, first call it I. So I'm going to call this I, and if you remember, we did this once before, because the way we're going to determine this integral is we're going to sort of use some sort of creative reasoning. We're going to come up with an equation where this integral shows up in multiple places, and we're going to sort of figure out that it's the unknown of an equation. So we're going to be able to deduce it that way. And so what you want to do is note that I is equal to the integral of so you want to think of it as this: secant x times secant squared x. You break it into two pieces. So that any power 3 can be written as power 1 times power 2. And then you're going to use some trig identities. So you want to use parts with u equals secant and dv equals secant squared x dx to get I equals secant x tan x minus the integral of secant x tan squared x dx. So you can fill in the details to get here. And then the next thing you want to do is you want to use the tangent squared is equal to secant squared minus 1 to get I equals secant x tan x minus I plus the integral secant x dx. And then solve for I. So that's the last thing you want to do. It's not an easy integral. It's a challenging one. And if you get stuck, check it out on the internet. This is one way to do it. Now, look, you're not going to follow what I just said because I left out a lot of the details. But if you listen to my advice, you can make it work. Does anybody have any questions about that? Yep, I can. By the way, this is a little sloppy. This is secant x down here. All right, any other questions about this secant cubed? This isn't the only way to do it. There are other ways of doing it, but this is one way. All right. So then the next question was, what's all the fuss about numeric integration? So well, let's sort of pick up where we were at when we last discussed this on Friday. All right, so here's what we did. We've been studying numeric integration. So numeric integration is the process of approximating a definite integral and so in this course we know we have 5 ways of doing this. I'm going to group them in a couple different classes. So I'm going to call the first ones 1, 2, and 3, and these are the left and right Riemann sums. and what we're calling the midpoint rule. And then the fourth one we taught you was the trapezoid rule. And then the fifth one was Simpson's rule. So the left and right Riemann sums go all the way back to Calc 1. We first encountered them when we were defining the integral. The midpoint rule is a generalization of them. And then, of course, the trapezoid rule and Simpson's rule are the new sort of, the new ideas here. So it's important to remember sort of what geometric object is in the heart of these. These are all done using rectangles. This is done, obviously, with a trapezoid. And Simpson's rule actually uses parabolas. Now, I am not suggesting you have to have these memorized. I'm not going to, obviously, I'm not giving you a timed in-class test, so you're not going to be asked to recite them. But I will say this, they're not hard to learn if you use them. You know, repetition breeds muscle memory, and that's not just with math, that's with anything. You drive a lot, you start to do things when you drive without thinking about them. You golf a lot, you start to get better at golf. You play tennis a lot, you get better at tennis. You play baseball or basketball a lot, you get better at it. How does a kid get good at walking? They freaking walk, right? That's how you get good at things. They become second nature the more you do them. I don't think that the idea is to memorize things as much as it is to understand how they are sort of developed. And then you can, even if you don't have them memorized, you can sort of derive them as you go. So what I mean by that is what we'll do on the next page. So if we want to put them down, so here's the goal. The goal is to approximate some integral. So the first thing you have to do is first, you need to compute your delta x. Your delta x is b minus a over n. So this means you need to decide how many rectangles or how many trapezoids or how many parabolas you're going to use. That's your n. Your b and a, you don't get to pick. Those are given to you when you're told what integral you want. So once you do that, then you compute what we call your partition. What is your partition? Your partition are the x sub i's. So what is the rule for these? X sub 0 is a. X sub 1 is a plus delta x. X sub 2 is a plus 2 delta x. And this pattern goes on and on. And the general pattern is that x sub k is a plus k times delta x. And then that goes down until you get to the last guy, which is x sub n. And x sub n turns out to just be a plus n times delta x. But that always simplifies to just b. Now, this is kind of the place where instructors would probably get annoyed, because this is one of the things that still confuses students in Calc 2, how to get these points, yet you've seen this now since Calculus 1. And so on one hand, it's like my opinion is, what have you been doing? How haven't you put aside the 20 minutes or the 2 hours that it takes to understand this? But then on the other side, I also realize, and I empathize with you, because I know it's hard. I know it's hard to learn this. And see, it's time for me to do my standard O'Grady, BI, whatever, is you can't, what happens so often in math is you guys let the notation win before you even try to learn it. So many people just look at this screen, or if this were on the board, and say, oh my God, I don't understand what any of this is, and then you just give up. And that's unfortunate that you give up, because you can learn it. It's just that for most human beings, it takes some considerable effort to understand this. It just does. You're not stupid. You're not, you're not in the wrong major. It takes considerable effort to learn this. I can't give you a simpler way of writing this down than what I've done here. We've done plenty of examples to help, sort of get you to understand where these things are coming from. But until you go and actually do it, knowing that the first few times you try it on your own, you're going to mess it up. It's just what it is. You're going to mess it up. And that's not just math. The first time you try anything, you're going to mess it up. Who's better at building a wall? Someone that builds walls all the time, or someone who doesn't? Who's better at laying concrete? Someone that lays concrete all the time, or someone who doesn't? Who's better at putting a roof on the house? Somebody who puts roofs on houses all the time, or someone who does it for the first time? Who's better at playing the trumpet? Someone who plays the trumpet all the time, or someone who just says, I'm going to try the trumpet tomorrow? Guess what? They're going to suck at it. Unless they're like some, special coming of Bach or some other legend. I don't know. The fact of the matter is, this stuff is hard to learn. Most things are hard to learn. They require effort, and they require the learner understands that you're not going to get it right the first time. Okay, so once you compute your delta x, and once you compute your partition, we're going to break a comma b into these n pieces. Once you understand that, then you just have to pick your favorite role. So let's remind you of what all these are. So we'll start with the left Riemann sum. This says that the integral from a to b of f of x is approximately delta x times a sum. What is it? Well, it's f evaluated at x sub 0 plus f evaluated at x sub 1, all the way up to the nth minus 1 point. That is the left Riemann sum. Now, I will quickly write down the right one so you can compare. This one, you start at the right endpoints, hence it's called the right Riemann sum. So you need to pay attention to where these guys, the first term in the sum and the last term, it is different in both of these cases. So this is your left. This one below it is the right. Now, as we alluded to, these are usually the least accurate versions. And we spent some time discussing why. And we're not going to spend any more time on that. We'll let you investigate that if you want. But part of the reason these are inaccurate is because if we're using rectangles, well, these guys, when you use these guys with rectangles, the way that these rectangles approximate a region, there's lots of room for error. And so one of the ways that you hope you might nullify that error is instead of using the left or the right of each subinterval, you choose the middle. And that's called the midpoint rule. Now, the midpoint rule seems great. The only issue with the midpoint rule, particularly, is that it requires an extra set of calculations. The midpoint rule says you don't add up the x sub 1, x sub 2's, but you add up these new numbers. And so let's remind you of what they are. What's m sub 1? Well, that's x sub 0 plus x sub 1 over 2. M sub 2 is x sub 1 plus x sub 2 over 2. These are the calculating the midpoints. And this, not only are these formulas scary looking, but it is also n more calculations you'd have to make. Yes? Well, it's not similar to the trapezoid rule. These are still rectangles. What do you mean by similar? No. So the 2's in the trapezoid rule show up in the actual formula. They show up here. These halves. So yeah, there's a 2 in the trapezoid rule, but the reason these halves show up here has nothing to do with why they show up in the trapezoid rule. So the question was, why do these 2's show up here? Well, I'm finding the halfway point between two numbers. How do you know the halfway point or the average of two numbers? You add them up and divide by 2. So these 2's that show up here have nothing to do with the 2's that show up in the trapezoid rule. So what's x1? x1 goes all the way back to the beginning. You have to compute your x values. X sub 0, x sub 1, x sub 2, all the way up to the nth term. So remember, if we draw a picture, what we're doing here is we have this interval that we want to integrate over. And it starts at A and it ends at B. And we want to break it into n equal pieces. So we partition it. And what are these partitions? Well, this is x sub 0, this is x sub 1, x sub 2, x sub 3. And so if you think about the distance between any two of these being delta x, then the way you can determine the values of these x sub 1s, x sub 2s is using this formula. So they're going to change depending on the context of the problem. But this general formula that we're looking at right here always, always, always holds true. So this right here would be the case n equals 4. Okay, so those are the 3 rectangle rules. Now, what we talked about at the end of last week were these more, what we would, I don't want to say sophisticated because they're not sophisticated really, but the idea was that we can cut down on error by using trapezoids instead of rectangles. So the trapezoid rule, and I'm not going to go in again to how this pops up. We've already done that, where these numbers come from. This rule, the first difference is out front is no longer just delta x, it's delta x over 2. That's the first difference. And then now, everyone but the first and the last term in the sum has a factor of 2 in front of it. And then a very, very close, I don't say very close, but a rule that's quite similar is Simpson's rule. And Simpson's rule has a pattern that is not the same, but somewhat similar. Instead of delta x over 2, it's delta x over 3. And this time, the constants alternate between 4 and 2. So once again, there's no constant in front of the first or last term, but there are constants in front of all the other terms. Say that again?
It doesn't have to end with a 4, right?
What do you mean? It absolutely has to end with, this has to be a 4 here, yeah. What do you mean it doesn't have to?
So what if it's a 2? Like if it's a odd number?
It's not going, well, it can't. So that's a great question. Don't forget, an important thing about Simpson's rule is that n must be even for this to work. You can't use odd. Doesn't make sense with odd numbers.
No, so what I mean is like before x n, right?
Yeah.
So it can be also 2.
No. It'll always be 4. Right? Because if n is even, that means the number of terms in your sum is going to be odd. right? So just take the simple case where n is 4. Then you have f of x sub 0, and then it'll be 4, 2, 4, nothing, right? And we did an example. I thought, did we not do one? We're going to do one anyhow right now. But I thought we did one on Friday. But if we didn't, we're going to do one right now anyhow. Any other questions on these things? So if the new homework asks you to write down the midpoint rule, trapezoid rule, Simpson's rule, and then it asks you to use them. So we'll do an example or two, and then you can mimic our fun here. By the way, problem 2 on the homework, I mean, we did that in class, so hopefully it doesn't give you too much of a headache. We already did it for you. As I said, you can use calculators for this. In fact, there's nothing wrong with it. And the more sophisticated that you are with a calculator, the easier this becomes. Particularly if you know anything about writing code, you can do this very, very quickly. I believe I showed you how to do this on Desmos, at least a shortcut for it. So let's do that again. Let's look at a pretty standard example. So this will be similar to your homework. So the first part we're going to do is we want to express log of, let's say, 3 as an integral. And then the next thing we're going to do is we will use Simpson's rule with n equals 6 to approximate the integral, and thus approximating the log of 3. So this is a very useful and interesting application of numeric integration. There are lots of numbers that can be expressed as integrals. And on your homework, we ask you to recognize that. And then that way you can get an approximation of that number and that when you get an approximation of that number, that being the integral, you can interpret it as a value of a specific number. So let's see how this goes. Let me get a different color here. So here's what we need to know. We know that the following. So the FTC says, it says that f of b minus f of a is equal to the integral from a to b of f prime of x dx. That's what it tells us. That's one of the ways to interpret the fundamental theorem of calculus. Now, of course, most students in calculus have a hard time seeing this, but this is in fact one of the things that it says. Now, I want to apply this formula specifically so that I can incorporate the natural log. In particular, if f of x equals the natural log of x, if a equals 1 and b equals 3, we have log of 3 minus log of 1 equals the integral from 1 to 3 of 1 over x dx. Or if you'd like, remember the natural log of 1 is, this is equal to 0. So you can immediately deduce that the natural log of 3 is this integral. So the moral right now is approximating the integral gives us an approximate value of the natural log of 3. So what you're seeing now is here's something that you've probably never encountered before. We are using our knowledge of integration to approximate numbers that we otherwise couldn't approximate. I mean, if I asked you what the natural log of 3 is, the only thing you could do right now is go plug it into a calculator. But what we're showing you is now here's a way to do it without a calculator. Now, technically, of course, we're going to use a calculator to do our arithmetic. But we could do what we're going to do by hand. So if we go back a previous page, we've answered part 1. So for part 2, we need to use Simpson's rule with n equals 6. So that's what we're going to do. Yes, go back. Let me know when you're ready. All right, so if we want to use Simpson's rule, we need to do some work beforehand. So to use Simpson, we start by calculating delta x, which we know is 3 minus 1 over 6, correct? 3 minus, because I said from 1 to 3. And of course, this becomes 2/6, which is 1/3. Then what are our x's? X sub 0 is 1. X sub 1 is 1 plus 1/3, which of course becomes 4/3. X sub 2 is 1 plus 2/3, which becomes 5/3. And then it's not hard to see what the pattern in x sub 3 is 6/3. X sub 4 becomes 7/3. X sub 5 is 8/3. And as expected, x sub 6 is 9/3. And why do I say as expected? Because x sub 6 should be the number 3. And last I checked, 9 divided by 3 is in fact 3. So let me repeat what I did here. I used the formula to get x sub 1, and then I got x sub 2 using the formula. And then right at that point, it was clear to me what the pattern is. And so then I can use my educated guesses to fill in the pattern. And being that the very last one agrees with what I knew it should agree with, I feel confident that my pattern's correct. Right, so okay, so if you're asking, the question is x sub 2 equals x sub 0. Well, it's x sub 0 plus 2 times delta x. So if you want to remember the general formula is x sub k is x sub 0 plus k times delta x. So this is the way I prefer to remember it. You can remember it any way you want, but that's how I like to do it. Well, yeah, you could do it that way, but yeah, you're not wrong. So the point Zafalger's saying is there's alternative ways of writing this formula. You're not wrong to do it that way. You can write it as x sub 1 plus k, or excuse me, x sub 1 plus delta x. That's just, I'm not choosing to write it that way. But you get the same thing. So the point I think you're trying to make is that you can write x sub 2 as x sub 1 plus delta x. Well, then you get the same number because that's 4/3 plus 1/3, which is in fact 5/3, which is exactly what we got. So it's two ways to calculate the same thing. Both your formula and my formula work. And really what it comes down to is the commutativity of addition. It doesn't matter what order you add in. Does that make sense? Very good. Yeah, so again, you're not wrong. It's two different ways to do the same thing. I just like this formula. It's my preference, but you can use whatever one works for you. Okay, so once we have this, here's what we know. Let's change colors. We now know that the integral from 1 to 3 of 1 over x dx, we know it's approximately delta x over 3, and then it's f of x sub 0 plus 4 times f evaluated at x sub 1. Well, let's be more clear, because we already know what f is, so let's maybe not write it out like, let's write it out a little cleaner. This would be 1 over x sub 0 plus 4 times 1 over x sub 1 plus 2 times 1 over x sub 2 plus 4 times 1 over x sub 3 plus 2 times 1 over x sub 4 plus 4 times 1 over x sub 5, and then the last one would be 1 over x sub 6. So notice that there's a 4 and a 2 in front of everything except the first and last. Now, at this point, as I pointed this out on Friday, you could go to a calculator and do all your arithmetic. I'm not asking you to do all this by hand, but I'm telling you could if you wanted to. So I'm going to go one more step of doing things by hand, and then I'm just going to plug it into a calculator. So before I go any further, does anybody have a question? So, like, for example, one thing that people will ask about is, why is it 1 over? Well, the reason it's 1 over is look at the function. The function is 1 over input. 1 over input. Okay, so now let's plug everything in. Out front, we end up getting delta x over 3, but since delta x is 1/3, this becomes 1/9. Then we're left with 1 plus, when I plug in x sub 1, that's 4/3. So when I invert it, I get 3/4. So I get 4 times 3/4 plus 2 times 3/5 plus 4 times 3/6 plus 2 times 3/7 plus 4 times 3/8 plus 3/9 or 1/3. So what I'm going to do now is I'm just going to go to a calculator. I mean, there's really, at this point, there's not much else I want to do other than have a software do the work for me. So I'm going to go to a calculator. So I'll use this one. I don't care what kind of calculator you use. I'll use the internet's calculator. Someone had a question. Did I make an error? No, you can't leave the answer like that. No, we got to get a. And now, what you should do, if you wanted to be like a true legend of these things, what you should do is you should probably, if you wanted to be like full math nerd, you could write this out as a decimal, which is 2077 1890. Barring that we didn't make any errors. Oh, yeah, question.
Is there a way where, let's say, if given n equals to 50 or 20?
Oh, you mean is there a pattern? I'm sure you can find one in there, but it's not going to be so obvious. It's much easier just to, write. Again, the question was, is there really a pattern that I'm ignoring? And I don't believe there's one here. I mean, there might be some pattern. Notice you could factor a 3 out of everything, but that's about it. It's not as the same pattern as when we had x squared, we had a clear pattern. So really the quickest thing to do is recognize that computers do arithmetic real good and we don't. So you have a computer do it for you. So what's interesting though is what's the decimal here? No, it's 2077. I'm sorry, Emily. Let me fix that. By the way, you should do this on your own and verify that you get the same thing I got. So let's put the pieces to this puzzle together on the next page. Before I leave this page, does anybody have a question? Oh my God, I'm losing my. So here's some fascinating stuff we just discovered. Here's what we just learned. So we just showed that the integral of 1 over x from 1 to 3, which we know is equal to the natural log of 3. We know it's equal to the natural log of 3. We just showed that this is equal to, the approximate value is, if we give a rational approximation, it's 2077 divided by 1890. But what is this equal to? This is approximately 1.0989. Now here's the fun part. Go to your calculator and ask yourself what the log of 3 is. So let's go to the Google calculator. If I go to Google, what is the log of 3? So let's go to our Google machine. And what's that?
It's 1.098.
It's pretty damn good, huh? Very good. So what does Google give us? 1.09861. 1.09861. So we are accurate to 3 decimal places. Pretty good. That's assuming Google's not lying to us, but they're not. So there's a couple cool stories we can share about this. And if you're thinking about, you might have a question, I'll share. You know, years ago, maybe 100, 200 years ago, long before calculators, what happened is we used to have to write books that literally just listed tables of values. There would be books that would have log of 2, log of 3, you know, log of 4, log of 5. And back then, it was probably not very obvious to most humans how other humans were coming up with these values. You don't think twice about it because you just plug things into a calculator and you're like, oh, okay, the square root of 2 is 1 point blah, or, you know, or the log of 3 is 1.098. But if I asked you, like, what is the numerical value of log of 3? Without a calculator, you wouldn't quite understand how to handle it. Now, there are other ways of doing it, but we just showed you one. And one of the things we're asking on your homework is for you to do this for the log of 5 and also for the arctangent of 1, because the arctangent of 1 is pi over 4. And so what you're going to do in your homework is you're going to actually, for the first time in your life, whether you realize it or not, you're going to actually calculate what the digits of pi are. You've just trusted someone that pi is 3.14 your whole life, but you've never had a way of verifying that other than that's what people tell you. So I hope that, that you take this into consideration, and let me summarize this a slightly different way. So let's say, I like to do this. I like to call this cool fact. So if, let's say A is any number greater than 0, you can approximate the log, in particular the natural log of A, this way. So the natural log of A is the integral from 1 to A of 1 over x dx, and you can approximate it. And here's the other cool fact that this is a hint for number 5 on your homework. The arctan of 1 minus the arctan of 0 turns out to be the integral from 0 to 1 of 1 divided by the quantity 1 plus x squared dx. Now, what you might not remember, and I will clue you into now, the inverse tangent of 0 is 0. The arctan of 1 is pi divided by 4. Now, this gives us an integral representation of pi. which means even if you don't know what the number pi is, the only reason you know is because you've been told your whole life it's 3.14 something, or you could plug it into a calculator. There's no reason that you should trust that other than all the people in your life say it. But now you can verify it. Because this means that pi is equal to the 4 times this integral. And so using numeric integration, you can approximate pi to any degree of accuracy. So it's hard for you to appreciate this being a Calc 2 student, but this is a big deal. I mean, I encourage you to think about what is the definition of pi. And every definition that you've learned about pi since you were a child had to do with the ratio of the circumference to the diameter of a circle. But nowhere in any of those definitions that you learned does it give you any insight onto what the size of pi is. What is its magnitude? What is its decimal expansion? Now, maybe if you had good teachers when you were a kid, they made you cut circles out of paper, and maybe they made you measure the diameter with a ruler and put string around the circumference. And maybe they showed you that, yeah, there's some number like 3.1 that seems to show up all the time. But there's really no reason to think that pi needs to be a certain value unless you really investigate pi in a much deeper sort of way. So, you know, I don't know that you gain anything, appreciation for what I'm trying to tell you. And if you do, that's great. If you don't, well, you can still do the homework. But, yeah, question.
So for the log, down the number will always be 1.
Say that again?
With the log of 3 or
Yeah.
so we need to always start from 1, going upwards.
Yeah, you go from 1 to 3. Or 1 to 5. Or,
Okay, so it will never be 0 or something, right?
well, no, it won't be 0 for log. Because, so why, you know, look, this formula, so the question is what's the lower bound? And for the logs, it's 1. And for the arctan, it's 0. And the reason is you want to choose these values to gain use. So when I go all the way back, to this page, when I say express log 3 as an integral, I'm using this formula. So I have to choose my function, and I have to choose my bounds A and B where they're useful. If I just randomly choose numbers, it does me no good. And I can't choose 0 here because the log of 0 is undefined. But why would I choose 1? I choose 1 because I know the log of 1 is 0. And the key to me choosing A equals 1 is so that this piece goes away. And then if it goes away, there's less things for me to worry about. In the next problem, why did I choose 1 and 0? Why would I choose 1 and 0? Because I know the arctan of 1 is pi over 4. That gets me pi. Now, I could choose any number I want over here, but then I have an arctan of that number, which is of no use to me. So why don't I choose an arctan that disappears? So if I choose 0, when I plug that in, I get 0. So I'm choosing it conveniently because it removes a term.
And when you're trying to find the arctan of 1, right? You have to use the 4 that was there.
No, I mean, when I'm trying, how do I know the arctan of 1 is pi over 4? Is that what you're asking?
No, the next one. You're over there, right? So when you're approximating, right? So how do you use the 4?
How do I use the 4? Just approximate the integral and multiply it by 4. That's it. It's pretty straightforward. You approximate this integral and then multiply it by 4.
But that's for the pi, right?
That's for pi. That's not for log, no. The 4 shows up because the arctan of 1 is pi over 4.
So what I'm asking is that similar to the next like 4 multiplied by the interval?
Yeah, I mean, this right here, this
Yeah.
is a direct consequence of this. If this is 0, it goes away, so I have arctan of 1 equal to this integral. But another way of writing the arctan of 1 is pi over 4. So this, if this is this in purple right here, is the same thing as this. It's 2 ways to write the same thing. I mean, I think what you're getting at is, I mean, you have to remember on the previous page, what I really have is I have this. So why not multiply both sides by 4? So I get an expression for pi. And so if I multiply both sides by 4, I get this. Does that make sense?
Yeah.
Any other questions out there in La La Land? Or is everybody sleeping? 15 sleeping Zoomers. All right, well, if that's the case, here we go. I'm not sleeping, I'm awake. That's what they always like to say. That's even better. I like that emoji. All right, listen, guys, thank you very much. We will discuss the midterm on Thursday. Please work on these homework problems. They're due Thursday, so if you have any last-minute questions, I'll answer them on Thursday. Otherwise, thank you guys very much. Have yourselves a nice couple days, and take care. All right, everybody, thank you. Thank you, thank you. You have to end recording.
So this